Hello friends, welcome back. Today we are solving a hard problem, Reconstruct Itinerary. We'll start with reading the problem statement and look at some examples to understand the problem. And next we'll look at what are Eulerian paths and use Heirholzer's algorithm to solve this problem, which takes linear time O of e, where e is the number of edges. And finally we'll write the Python code for it. Let's get started. We are given a list of airline tickets where tickets of I represent the departure and arrival airports of one flight, where the first element is the departure airport and the second element is the arrival airport. We are also given that all these tickets belong to a single person, which basically means these are all the tickets a single person used on his journey. And the goal of this problem is to reconstruct his itinerary or journey in order. We are also given that he departs from JFK Airport, hence his route must begin with JFK. If there are multiple valid routes, we should return the route that has the smallest lexical order when read as a single string. Here is an example to understand what is smaller lexical order. These are the two routes we are comparing right now. The first airport in both the routes are the same. Let's look at the second airport. Second airport of route 1 is LGA and the second airport of route 2 is LGB. Since A comes before B in the alphabet, route 1 has a smaller lexical order than route 2. Now, the question also states that we may assume all tickets form at least one valid route and we must use all tickets once and only once. Now let's take a look at these two examples. Just to recap, all these tickets are given to us in random order, and the goal is to construct a route using all the tickets once and only once. If there are multiple routes possible, we need to return the route that has the smaller lexical order. In the first example, the first ticket is from MUC to LHR, which is this edge. Second ticket is JFK to MUC, which is this edge. Third is SFO to SJC, which is this edge. Fourth is LHR to SFO, which is this edge. As you can tell already, it becomes easier to find the route if we can build a directed graph using all these flights, where nodes are the airports and the edges are the flights themselves. Once we build a graph, the goal is to find a route that starts from JFK and visits all these edges once and only once. And in example 1, that route is from JFK to MUC to LHR to SFO and SJC. We visited all these edges only once, and that's the output we see over here. Similarly, in example 2, we start from JFK to SFO, SFO to ADL, ATL to JFK, JFK to ADL, and ADL to SFO. That's one route that starts from JFK and visits all the edges. Let me write down the route here. I have written down the route here. But there is a second route in this graph, which is JFK to ADL, ATL back to JFK, JFK to SFO, SFO to ADL, ATL back to SFO. That's the second route. I have written down the second route over here. Whenever there are multiple routes possible, the problem statement says that we have to return the route that has smaller lexical order. In this case, route 2 has smaller lexical order because the second airport in route 2 is ADL versus second airport in route 1 is SFO. A comes before S in the alphabet, hence we return the second route, which is the output over here. Before we look at how to solve this problem, if you haven't subscribed, please do, because it helps us in a big way to make more content like this. Next, let's look at what exactly are Eulerian paths and how do they help in solving this problem. An Eulerian path in the context of a directed graph is a path that visits all the edges exactly once. which is exactly what we want to solve this problem. But the question is, can an Eulerian path exist in all directed graph? The answer is no. For the Eulerian path to exist, these three conditions have to be met, where all the nodes should have the same in degree and out degree except for these two nodes. Out of the remaining two nodes, one of them should have out degree minus in degree equal to 1, and the last node should have the in degree minus out degree equal to 1. In this example graph, these nodes have the same in degree and out degree, and there's one node that has out degree minus in degree equal to 1, and there's the last node that has in degree minus out degree equal to 1. So in this graph, there's definitely an Eulerian path. But for the given question, we don't need to check if an Eulerian path exists because the problem statement already says that there's at least one valid route. So given a graph like this, how do we find an Eulerian path? Can applying a plain depth first search yield an Eulerian path? Let's find out. We always start depth first search from a node that has one more outgoing edge than an incoming edge, in this case node A. We go from A to B. From B, there are two possible routes. We take B to C, C to E. From E, there is nowhere else to go. We backtrack to C. From C, there is one more outgoing edge which goes back to B, but B is already in the current path, so DFS does not go back to B again because it's in the current path. So we don't explore this path. There are no more edges left from C, so we backtrack to B. From B, we take the other route now to D, and from D we go back to C. From C, we go to E again. E does not have any outgoing edges. We backtrack to C. From C, we cannot take this route again back to B because B is in the current stack. So we backtrack from C to D. There are no more outgoing edges from D, so we backtrack to B. We have explored all the edges from B, so we backtrack to A. So in this entire DFS, we did not explore this path at all. Hence, applying a plain DFS will not yield the Eulerian path. What changes can we make to the DFS so that we can explore this path as well? Which brings us to Heirholzer's algorithm. Heirholzer's algorithm is based on depth first search algorithm we just saw, but the only difference is instead of adding the node to the output as soon as we get to it, we add the node to the front of the output once all its outgoing edges are explored. Let's see how this works. We start from A as before. We don't add A to the output just yet because we have to wait until all its outgoing edges are explored before adding it to the output. So we go from A to B. From B, there are two outgoing edges to C or D. Let's say we go to C. From C, we go to E. From E, there are no more outgoing edges. We add E to the output and backtrack to C. I've added E to the output over here. From C, there is another outgoing edge to B, so we go to B. From B, there is a second outgoing edge to D, so we go from B to D and D to C. Since there are no more outgoing edges from C, we add C to the output and backtrack to D. I've added C to the output over here. From D, there are no more outgoing edges, so we backtrack to B and add D to the output. I've added D to the output over here. From B, there are no more outgoing edges, so we backtrack to C and add B to the output. I've added B to the output over here. Again, from C, there are no more outgoing edges. We backtrack to B and add C to the output. I've added C to the output over here. We're back at B again, and there are no more outgoing edges, so we backtrack to A and add B to the output. I've added B to the output over here. Similarly, there are no more outgoing edges from A, so we add A to the output and our algorithm ends here. I've added A to the output over here, and this is a valid Eulerian path. But there is another Eulerian path that goes from A to B, B to D, D to C, C to B, B to C, and C to E. This is the second Eulerian path. But we still return the first Eulerian path because if we look at the first difference between these two paths, which is C and C comes before D in the alphabet, so we return the first path. So that's the final algorithm to solve this problem. We start from JFK and run Heirholzer's algorithm to find the Eulerian path, which is the itinerary or the route that starts from JFK and visits all the edges or takes all the flights. The runtime of this algorithm is big O of E, where E is the number of edges because we visit each edge only once in this algorithm. Let's write the Python code for this algorithm. First, we start by building a graph, which is an adjacency list. G equal to default dictionary, which is a list. Then we go through all the tickets and add them to the adjacency list. For A, B in tickets, A is the from airport and B is the to airport. So we need to add B to the adjacency list of A. So G of A dot append B. Since we need to return the final route that has the smaller lexical order, if we sort these nodes in the adjacency list, then we would be exploring the nodes that has the smaller lexical order anyway. So let's sort these nodes in the adjacency list for key, value in g.items, where v is the list of nodes. We just have to sort v. Next, let's define the output array to store the result, and then we have to start the traversal from the JFK airport because the problem states that we need to start our journey from JFK airport. So let's start traverse from JFK. Let's define this function traverse airport. We need to explore all the outgoing edges of this airport once and only once. So while G of airport, we need to get its neighboring airport, which is NEI equal to G of airport pop 0. We're popping the first airport in the adjacency list, which has the smaller lexical order anyway. And we are popping this from the adjacency list because we can only use this edge once. Then we call traverse on this neighboring airport. Once we are done exploring all these outgoing edges, we need to add airport to the result. Result.append airport. Only thing we need to do before returning this result is we need to reverse this result array. Because instead of adding this airport to the front of the array, we are appending it to the back. So we just have to reverse it before returning. Result.reverse. And then we return this resulting route. Let's try to run the code. As you can see, the submission goes through. I hope this video was helpful. Thanks for taking time to watch the video. Take care.